Start here, circumference. Going to start day one, moving on. All right, day one all the way through. Circumference of a circle. Let's roll. 14, circumference of a circle. 2 pi r. Or you can also remember, what's the other one? Anybody? Pi d. All right, next one. I got angle AOB. You can either name it, don't call it angle AOB, but name it what it's called in a circle or how to find it. Okay, those are your two options right there. Tell me what type of angle it is or how to find it. Angle AOB, that is the center of the circle, by the way. O is the center. So either what type of angle is it or how to find it. Let's roll 10. Okay, angle AOB is the same as the measure of arc AB. And then what's it called? Central angle. All right, central angle. Because where's the vertex? It's in the center. All good there? Okay, moving on. This comes from Friday's notes. Length of an arc. If the angle is in degrees, you do the measure over the arc over 360 times circumference. That's if the angle is in degrees. And then on Friday you learned, well, not all angles are in degrees. They're sometimes in radians. If that's the case, S, which is the arc length, will be equal to the angle in radians, theta, times the radius length, SOR, whatever you want to refer to it as. Arc length is equal to the angle in radians times the radius. We all good there? All good? Yes, Teddy. If you want to do it that way, I'm okay with that. Because if you only want to memorize one formula versus two, just not my worry, but make sure you can convert. All right, you got to have the ability to convert back and forth. Speaking of converting, how do I go from degrees to radians? I can multiply, and this is on your formula sheet, and I know it's very easy to say, oh, it's on my formula sheet, I'm not going to worry about it, but you got to know which one it is on your formula sheet, okay, because it's either 180 over pi or pi over 180. You got to know which one you're using on the formula sheet. It's great that it's on the formula sheet, but you got to know which one to pick. So degrees, so I have degrees, and I want to change it to radians, so I multiply by 27, multiply by, there you go, pi over 180, and I won't ask anybody the next one. Multiply by 180 over pi. All right, and I'm not going to ask the rest here. Don't get nervous. That's coming up tomorrow. Okay? But anything so far that we've done before I start going into the homework? All right, let me start with Thursday night homework, which I have not checked yet, which is converting degrees to radians, radians to degrees. I believe we're on page 9, I believe. 9 was the homework on Thursday night. Radians to degrees, degrees to radians, and then also this clock question, and there will be a clock question on Thursday's quiz. Okay, here's the time. What's the angle of the minor arc? Yes. Number 5, you got it. So we have, what do we have? 4 pi radians. So if I want to go to degrees, I multiply that by so I have 4 pi. Conversion is multiply it by 180 over pi. Pi's cancel. And I have 720 degrees. Okay, and yes, I know it may seem a little strange, but you can have an angle bigger than 180, bigger than 360. Okay. All right, good conversion there. Anything else on that homework assignment before I get to the tougher questions? All right, and then Friday was going back and forth between the two formulas. So let's take our time here. I copied all of them, so wherever you want to go. All right, I don't want to go through all of them, but I have copied all of them, so wherever you want to go. Maggie, start. Number 2. All right, here's number 2. Let me go slowly through number 2. Because first, I think the question itself was difficult to understand what we were looking for. First, every single scenario, the circle is going to have a radius of 12. Every single scenario. So the first scenario is saying, all right, you have a central angle of 120 degrees, and an arc length of 8, radius of 12, will that result in an arc length of 8 pi? That's what you had to check. Radius of 12, angle measure of 120, will that result in 8 pi as the arc length? All right, well, what's your central angle in degrees or radians? Degrees. So I'm going to use the formula that uses degrees, which says the length is equal to 120 over 360 times pi. What's my diameter if the radius is 12? 24. And if you calculate this, reduce 120 over 360 times 24, you will indeed get 8 pi. So that checks out. All right, that checks. But I'm looking for the one that's incorrect. Everyone good so far? All right, then get rid of that. Now let's go to scenario 2. Now my angle's 6 degrees. Not 6 degrees by drawing the scale. 12 for the radius. Will that result in an arc length of 72? Okay, ready? 6 over 360 equal to pi times still 24. But if you do that, I don't think it comes out to be 72. I don't think it comes out to be anything close to 72. So that one's incorrect. All right, just let me go over 3 now. All right, let me go over 3 and why it works. Now what's my angle in number 3? 2/3 of a radian. Radian. So instead, now I want to use S equals theta r, where theta is now what? What's my angle in radians? 2/3, no pi, just 2/3, radius of 12. And if you do 2/3 of 12, you get out 8, which that's what it says it was. Okay? And if you did 4 with S equals theta r, it would have came out to be the same. Maggie, we good? Yeah. Everybody else, we all right there checking those different scenarios. 2's the only one that didn't come out to be what the arc length should have been. Let's go. Let's go. Where else here? I'll stop and go over a couple and see how you did it then. I don't really want to go that route, but especially with those last 2, there's a hint there. Emma? 5. Here we go. Good question. Find the length of the major and the minor arc, round to the nearest tenth. All right, let's start with the major arc. Let me highlight it real quick, everyone. Find the length of this major arc. What's my angle in, first of all? 5 pi over 3, radians or degrees? Radians. Now, Teddy just suggested, hey, if I want to use just this formula the entire time, fine. But you got to make sure you can convert. If you want to use this formula, you have to convert 5 pi over 3 to degrees. That's your call, though. I do not care which one or if you memorize both. All right, just be prepared to convert if you're only going to memorize one. All right, I'm always going to memorize 2, so I'm going to use S equals theta r here. So S equals, what's my angle measure? 5 pi over 3. Radius length, 5.62. I just plug it all into my calculator and round to the nearest tenth for the major arc. Minor arc's a little more work. All right, minor arc's a little more work. Okay, here. Now to do the minor arc, you need to find that angle right there. Degrees, radians, your call. All right, we have not gone over how to use the other angle to get to the smaller one with radians. So instead, what I'm comfortable with you guys doing is taking 5 pi over 3, converting it to degrees. How do I convert it to degrees? 180 over pi. Gone. Oh boy. 300. Okay, so if that's 300, what's that angle if they all add up to 360? 60. So I know this angle is 60 degrees. So I could use my measure over 360 times pi d, or I could convert it back to radians. I don't care. You're just going to get the same answer. Why? My point of view, why waste an extra step converting it back to radians when I have a formula for it already? So I'm just going to say 60 over 360 times pi. What's my diameter if that's 5.62? Woo. 11.04? 24? 11.24. Plug it in my calculator, round to the nearest tenth. All right. Anything else? So we clear on these 2 formulas. I don't care. I'm not going to give you either one. You can memorize both, or you can memorize one, but make sure you can convert degrees to radians, radians to degrees. That's my concern. Anything else you want to ask? Because we're getting away from arc length today. Getting away from it. Big part of Thursday's quiz, though, but getting away from it. What's up, Maggie?
So for that one, could you have found the circumference of the circle and then found the length of the major arc?
You could have. That's a great idea. It's a great idea. Never thought of that. Perfect. Nice job. Everyone hear what you said? Because it was pretty good. After you found the major arc, you could have just found the circumference and subtracted the major from the circumference to get the minor one. Nice job. Yep. Makes mine seem a lot more work. Other questions? All right, let me see. Can I see both nights, please? It's really just the packet, so pretty easy to show me. Oh, are we in for a treat here? Are we in for a treat here? What? Okay, I don't know what's happening there. All right, anyway. A lot of facts I'm going to throw at you today. Not that you don't have enough already, right? In this circle unit. The reason I am giving you these facts is because tomorrow, these facts will be going into welcome back, the reasons column of your proofs. Statements, reasons, and I don't know if it's good. It might be a good thing, bad thing because they're coming back. Good, it's the last unit we do proofs in. This is it. Last proofs, last construction unit. Okay, and that's it. So, all right, before we can get back into the proofs, though, we need to make sure we get a solid understanding of these new facts here I'm going to throw at you. Before we start even any of the new theorems, right above there, top right-hand corner, draw me a circle. Please, no compass needed, just freehand a circle. And I'm going to put a center in your circle, please. And I just want to be confident in your abilities. I'm going to walk around. Can you please draw a chord and a diameter in your circle, please? So I know you know which one is which. Okay, so please draw a chord and a diameter. You could kill two birds with one stone, yes. Okay, we're good. Making sure your diameter has to go through where? It's got to go through the center. Chord does not. But somebody could have just drawn a diameter and that could have satisfied both. Diameter, longest chord in a circle. Okay, good job, everybody. Okay, here we go. Bless you. Theorem 1. Everyone's got a circle. Here we go. Theorem 1. Everyone has a circle. What I'd like you to do first, place a center in that circle, please. Name the center however you want to name it, because that'll name the circle. And what I'd like you to do right now as I walk around here, draw two central angles that look about the same length, in the same measure. Okay? Draw in two central angles. Label them with letters too, please. Mark them congruent. Two central angles. Two central angles. Label them and make them congruent with the appropriate markings. All right, here's the first theorem. If the central angles are congruent, so are the arcs that belong to them. All right, so in my case, I have these two central angles that are congruent. this theorem tells me that arc AB is congruent to arc BC. Name your arcs however you labeled them. All right, so here all I'm going to put under number 1 for me is that tells me that arc AB is indeed congruent to arc BC. And again, don't use AB and BC if you didn't use it on your own diagram. Use the letters, please. Bless you. If the central angles are congruent, bless you, so are the arcs. And we're not going to draw another circle again, but the reverse is true. Take a look at number 2 underneath theorem 1. If the arcs are congruent, so are the central angles. No, hey, I'm serious. Get out of the habit of saying angles. Because right now, yeah, you only have central angles, but on Wednesday, you're going to have a different type of angles. Okay? All right, so start saying central angles for me. We good on theorem 1? All right, let's go to 2. You have your own diagram there. Again, place a center in your circle. Name that center. Draw 2 chords right now. Label the vertices of those chords and mark them congruent. 2 chords, everybody. Chords. 2 chords that look congruent. They can intersect. All right, they don't have to. They can be on opposite sides of the center. It's up to you. And again, mark the chords congruent with hash marks. Second theorem. The chords are congruent, so are your arcs. Chords are congruent, so are the arcs. So in my case right here, since chord AB and chord BC are congruent, that tells me arc AB is congruent to arc BC. Again, whatever letters you guys use, please use them. What? Are you done? Yeah. Okay. Opposites true. Arcs are congruent, so are the chords. All right, most of these we can go back and forth. Third one is huge. This third one. Don't need a diagram, provided one for you. What is ADB up here? Don't say a word. Here we go. ADB, name it. Here we go. 16. What is ADB, that segment in the circle? It is a diameter. Somebody tell me what CFE is in the circle. 3. What is CFE in that circle? Chord. I have a diameter and a chord. And what do you notice here? Perpendicular to each other. So if I have a diameter and a chord perpendicular, look what happens to the chord. It gets bisected. Not the diameter, the chord gets bisected. So using the diagram right now, tell me 2 segments that should be equal now. If a diameter and a chord are perpendicular, the chord gets bisected. So which 2 segments up here are 13 congruent? There you go. And in addition to that, so the arcs get bisected too. So we know that arc CA is going to be congruent to arc AE. Okay, not only does the chord get bisected, so does the arcs. And I'll tell you, we don't really use the arcs getting bisected too much. It's the chords. That's where we make our money here on this theorem. The chords getting bisected. Watch this for me. I want to make a huge point here. It is very rare in a diagram that we'll see the full diameter drawn in. Ready? What's this part right here? Okay, this still applies, this theorem. It doesn't have to be a full diameter drawn in. All right, as long as it's part of a diameter. Ready? Watch. You may just even see that part right there. That part from D to F, is it still part of a diameter? Then the theorem still applies. Very rare you're going to see a full diameter drawn in. But if it's coming from the center or through the center, perpendicular to the chord, this theorem still applies. We okay there? Because you're not going to see the full diameter every time. Questions, comments, or concerns before we get to the last theorem? Whew, all right. You're on that. Ready to hand it to me. Ready? Last one. 11. What's ED in this diagram? It's good too. It's good too. 28. What is ED in the diagram? It is a chord. What is CB in the diagram? 23. What's CB? Also a chord. How far apart are both chords from the center? 8 units. The same distance. Instead of same distance, we have a big boy, big girl word, and that is equidistant. If two chords are equidistant from the center, they are congruent. So in our case here, chord DE is congruent to chord CB. They're equidistant. Now, I'll either put the distance on there, or how else could I show you they're the same distance away? You see the little hash marks going on, all right, instead of the actual length. Whew. All right, that's it. We ready to apply these now? These are not proofs. Let me emphasize that. These are not proofs. This is me giving you information, you spitting out as many true facts as you can for me to get practice for tomorrow. All right, these are not proofs. I'm going to give you that the two circles are congruent, and arc PU is congruent to PR. Arc PR is congruent to arc SU. What can you give me in return? If those two, the circles are congruent and the arcs are congruent. Let me start with the arcs being congruent because that's pretty powerful. If those two arcs are congruent, what else must be congruent based on some theorems we went over today? Name a pair of something, angles, side segments that are also congruent because the arcs are congruent. Let's roll 30. Got anything? Okay, PR, that is true. Now we'll write a reason we're going to write tomorrow. So PR is congruent to SU. Paige, what did you just give me? No, hold on. I don't want you to spit it out. What are PR and SU? They're chords. How'd you know the chords were congruent? Because the what were congruent? So I'm going to start this out by saying congruent arcs, because that's what I was given. Imply congruent, Paige, what you just give me, congruent chords. And that's what we're going to write in our reasons column. There should be another pair of congruent somethings up here because the arcs are congruent. Dan, what do you got there, stud? Angle Q congruent to angle T. Nice job. What did you just give me there? What are Q and T? What are they? How'd you know they were congruent? Because I gave you congruent arcs imply congruent central angles. And again, you have to have that word central in there. Nice job, kids. There's one more I'm going to put in here, though. And we didn't bring it up today in the theorems at all. There's something else up here that's true, and we haven't brought it up in the theorem, so if you didn't know, that's fine, but get in the habit of seeing this as well. Question, Emma, first. Stop. That's how it. Because it's the okay, it's a central angle, yeah. Okay. I wouldn't be talking about anything bigger than 180. So, okay. Good point. What, Meg? Which ones? Good job. What are PQ, QR, ST, and TU? Radii. And this is going way back to the first day of this unit. I told you the circles are congruent. Anybody know two circles are congruent if they're? Ooh. If two circles are congruent, only if the radii are congruent. All right, so if the circles are congruent, that tells me PQ is congruent to QR, is congruent to, all four are congruent. ST congruent to TU. And how did I know that? Congruent, what was I given? Congruent circles imply congruent radii. Whoa, no, don't even go there. I know where you're going. I know where you're going with this. Why can't I use the circle symbol instead of writing out the 7 letters it takes to write circles? All right. Yep, it's so tough. My wrist is killing me. I don't know about anybody else from writing that. It's killing me right now. We're good. Honors kids, we're good. Yeah, go ahead, killers. What do you got back there? You could put that too, yeah. Yep. You could do that, yeah. Yep. Anything else? Okay, and then 2, circles are congruent. BC now is congruent to KL. BC and KL. What other pieces are congruent then? 23, you're up. What other pieces? If BC and KL are congruent. Yep. Arc BC is congruent to arc KL. Now, be careful how you write this. What did I give you? What are BC, line segment BC and line segment KL? So you're going to start this reason off by congruent chords now. Always start it off with what you're given. Imply, what did Kate give me back there? Congruent arcs. And then if the circles are congruent, what else are congruent? The radii. So BA, congruent to AC, congruent to KJ, congruent to JL. Congruent circles. Whew, ow. Imply, I'm rubbing it in. Congruent radii. And then yes, if anybody wants to go hardcore and say angle A congruent to angle J, congruent arcs imply congruent central angles, that's fine. All right, I'll leave that off. I think we've had enough here. So we okay on these theorems here? Because now we got to use them algebraically. Solve some algebra problems, which aren't too tough.
Was it the guy? I called it. Curtain. Every single time, get it. I think it comes down to any mean model.
All right, here we go.
Wait, remember last time we got checked? Remember last time it was something you didn't put it up.
What do you mean? I got another slide after this. We're good. We ready here? Guys have been slacking lately. Since probably the first quarter. Cube. Cube. Star. Flip. Curtains. Curtains, curtains. Hold on, curtains. Star. Fade. We just had that today. Clock. Things don't come up twice. Okay. Shatter. Genie. Slide right. Slide left. Pinwheel. Any drops? All right, you ready? You got Promethean Man or you got the genie coming down? Here we go. There you go. It never comes up again. It was already today. Yep. Okay. Yep, there you go. Never comes up twice. Yep. Should listen. All right, let's do this. Good try. Whew, boy. Rough times here. All right, find the value of x. Let's take a look. I have a right triangle built into there. 8 represents the entire chord length. Hi, Sinead. Didn't it come up here twice?
No, like one after the other.
I don't know. Understand the question.
You got Promethean Man.
Yeah.
Promethean Man was like right after.
It was the winning one,
and it
so
was
they
like,
have one.
yeah.
2 in a row.
Yeah.
Yeah. Didn't that happen this year in here?
It was we guessed.
You guys have always guessed the next one? Oh, well, yeah, it's yeah. 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 Promethean Man's come up twice. Yeah. Oh, yeah. Yep. Yeah. All right. Moving on. This chord is a length of 8. This is exactly what I was talking to you about with the theorem earlier. Is a whole diameter drawn in? No, but everyone take a look. X is part of a diameter. Take a look. X is part of a diameter. So what's it doing to the chord? It is bisecting it. That is where this theorem applies. You're not going to see the whole diameter drawn in. You see part of the diameter since it comes from center C. So that still counts towards the theorem, which says it bisects the chord. So now the 8 gets broken up into 4 and 4. And now how can I find x? Pythagorean theorem. X squared plus 4 squared equals 5 squared. I'll let you guys go ahead. I know it's a classic triple, but and the value of x turns out to be 25. 3, good. Now the work or reason used, what was the only theorem we used here? And let's get practice writing it out. How did I know it bisected? Ready? A diameter, and you can write diameter. I know there wasn't one drawn in, but it's part of a diameter. A diameter perpendicular to a chord does what? Bisects the chord. That's a lot. It's a pretty powerful one here in this unit. And 4. What are you doing here to find x? Whew. Finding the length of the chord. There's nothing perpendicular to it, so can't bisect it. Anything here? What's up, Maggie? Settle down.
Well, there's a second radius.
If that's 6, that's a radius, so any radii I draw in will also be 6. We'll write that theorem down in a second, but yes, this side will also be 6. And now you could do once again to find x. Pythagorean Theorem. 6 squared, yes, and I do want it in simplest radical form, please. 6 squared plus 6 squared equals x squared. So you're breaking down 72 for me. It is also 45, 45, 90, so you can apply your rules there, absolutely. And in simplest radical form, that hypotenuse, that chord 30, 6 radical 2. All right, real quickly here, this is going to be a new reason we're going to write down. How did I know that other radii was 6? Okay, I like that, but that's not true. Ready? In a circle. In a circle, all radii are congruent. Do we see how important it is to have in a circle first? Because I cover that up, all radii are congruent. Is that a true fact? Every single radii? No. All right, it's got to be in a circle. All good? One more. Glad we're getting real versed in the transitions. All right, next one. There's actually 2 theorems I want. Before I talk about each piece here, these 2 chords are how far from the center? 7 units. They're equidistant. If I have 2 chords that are equidistant, what do I know about their lengths? They are congruent. So this whole chord is 7. So that's 2 chords equidistant from the center. Just want to use every theorem we can. Equidistant from the center are congruent. That doesn't answer the question, though. How do I find each piece, then? Actually, it's not 7. Calm down, everybody. No one was going to... Thought you guys would be all ready for that. You smelled blood and didn't take advantage of it. You're bad. How do I find each piece? How do I know? Oh, that's easy to say. It's 3 and 3, but how do you know? Here we go. Diameter. Perpendicular to a chord. Bisects the chord. And that's where we finish this off by saying x is equal to 3. All right. Not much. A few algebra problems out of the book tonight, and then we get into proofs tomorrow.